First thing I want to mention is that, so hopefully you enjoyed your week break. As far as lab goes, group two from Thursday's lab obviously has a certain disadvantage because we missed both that week and this week. So definitely Thursday's lab will be a chance for group two to do lab two. As for everyone else, anyone in group one or anyone in the Wednesday lab, that will be a chance for you to say, come in and make up any lab you may have missed. So lab one or lab two, and we'll just be back on schedule next week. At least that's the goal, to be back on schedule next week. We'll just continue with lab 3 instead of lab 4. Now, if you want to come in and get help with homework or ask questions about the test, you are free to come in so long as you just at least mask up. You don't need to be like fully goggle safety. I'm sure there'll be room in the lab, but you can come in during that lab period. I will be there for at least an hour, if not the full 2 hours. If I have people show up, I will be there the whole 2 hours. If no one shows up within the first hour, I'm probably gonna boogie. But so that will be the plan for lab. I will go ahead and post this on the Google Classroom, both for the lab and the lecture, so that everyone gets the idea, even the people who aren't in this lecture, so they know. But that is the current plan. If you have a lab 2 done or a lab 1 done and I haven't gotten that document, make sure you get it to me. If you don't have a score currently posted for like lab 1 for any of the things, it's because I'm missing some part of the lab. I'd like to get that in. Technically, I've already posted the 6-week grades. They're a rough grade. If I don't have any points for you, obviously you're not doing good, even though I dropped the lowest lab. So some people have done lab 2, but I don't have their lab 2 report, and they missed lab 1, so they have technically almost no grades in here, even though I dropped the lowest lab. So also be thinking about the online labs. I only have one really online lab from a person or two. So don't put that off to the last minute. They shouldn't be too hard. What I'm looking for is just a short video where you answer the question. Short video where you answer the question. On the video, I don't need a document. I don't need to see you doing all the like steps, especially if they're like tedious steps and they don't need to be done a lot. Just a quick heads up, like someone did the vitamin C lab. We don't need a whole banana, just a couple slices is fine. We don't need 3 apples. We just need a slice here and a slice control. And ideally, I'd like to see that one like before and after kind of thing. But just for future note. But it's not meant to be hard. I'm not meant to take a ton of points off or anything like that. So it's easy to get the full points. And the people who did that one did get the full points. So with that in mind, something to keep in mind for lab. Now, going on with lecture. So remember, we completed chapter 14, chapter 15. That is the test 2 material that'll be due on Friday. Be working on that. If you get it done sooner, great. Send it in. But if not, we'll worry about that. Okay. Starting chapter 16, which is going to be acids and bases. We've kind of talked about acids and bases before, back when we looked at like chapter, depending on which book you used, it's either chapter 4 or chapter I'd like to say not 8 or 9. It doesn't really matter, but the whole idea is we looked at it when we looked at aqueous chemistry. Now, ideally, we're going to look at this a little bit more in depth, and specifically about acid bases and less about precipitation. Now, an acid, first let's define what is an acid and what is a base. We're going to have a couple different definitions that we're going to go through as we progress. Start with the simplest and work our way to the most complex. But each time we're going to be expanding the Venn diagram of what we understand as an acid. So we're going to start with narrowly defining it and slowly working our way outwards as we better understand this. But they knew about acids back, the ancient Greeks knew about acids and bases. Just in the name, some of the stuff, aqua regia, which is one of the strongest acids we have, which is like nitric mixed with sulfuric, I think, if I remember right, which is what, like Latin for the water of kings, because it could melt gold. It could dissolve gold. King's water. But acids, by characterization, are typically sour. Now, I wouldn't suggest you sticking your finger in hydrochloric acid and sticking on your tongue, but you've all tasted vinegar. You've all tasted citric acid, whether you've eaten a lemon or you just even had a glass of orange juice. Acids are sour in taste. Bases, now you may not have had very many bases, but if you've had, like, say, milk of magnesia or some like Maalox, some antacid, they are typically very bitter in flavor. By their very nature, acids will cancel out a base and bases will cancel out of acid. The first definition we're going to go through is the Arrhenius acid and base. Arrhenius, remember, we had the Arrhenius equation not that long ago in chapter 14, that equation that looked at kinetics. Well, he did also some work with acids and bases, and he defined specifically an acid is just something that will increase the amount of protons when dissolved in water. Anything that's going to produce H plus when we dissolve it in water. And then base, the Arrhenius base, would be anything that would increase the amount of hydroxide when dissolved in water. So typically you can tell an Arrhenius acid or Arrhenius base just by looking at, is there an H in the formula? Is there an OH in the formula? This will work with many of the things. If I say sodium hydroxide, well, that's obvious a base. Hydrochloric acid, HCl, that's clearly an acid. But that doesn't really cover a whole lot. We have our basic strong acids, our basic strong bases, but that really doesn't cover the whole scheme of things. So we'll probably jump right in to the next definition. That typically when a proton forms in water, it will react with the water itself to produce something we call hydronium, which is H3O plus. This is the only other really carbocation, polyatomic carbocation that, well, not carbocation, the polyatomic cation that we'll see other than ammonium. But HCl, when it mixes with water, we add a H plus and it becomes H3O plus. This forms whenever we mix an acid with water, no matter what. We are going to use this interchangeably with H plus or H3O plus. Those are pretty much the same thing. H3O plus is really the more accurate way of looking at it. But for the most part, you can think of it the same way. Now, an acid's degree of dissociation in water will lead to its classification as a strong acid or a weak acid. We talked about this last year when we talked about strong electrolytes and weak electrolytes. Strong electrolytes produce lots of ions and conducted electricity really well. Weak electrolytes produce little amount of ions and conducted electricity very weakly. Now that we understand equilibrium, we can actually define this, that a strong acid would have a K that is much, much greater than 1. In fact, we usually say K is over 100 or more. If the K is over 100, that means it's going to dissociate nearly completely. Will an acid ever dissociate completely? No. But 99.9% dissociation is essentially 100%. But there's only really 7 strong acids worth knowing: HCl, HBr, HI. Nitric acid, which is HNO3, perchloric acid, chloric acid, and sulfuric. Those are the main inorganic acids that we'll deal with. Some people will say chloric acid, HClO3, is borderline strong, maybe a little bit weak. And you could probably say perbromic acid, periodic acid, but we're not going to really worry about them. We don't really see them very often. These guys are the ones that are going to be seen very, very often, and so worth knowing. But looking at this, so the strength relates to their degree of dissociation, which is we're going to call the Ka, and we're going to talk about it. Strength is not concentration. The strength is all the degree of dissociation, because you can have a very concentrated weak acid that is not as dangerous as a dilute strong acid, because if you only produce 1% of the ions you have available, even if you have 10 times the concentration, 1% of 10 is still your 10 times as your 10% as strong as the strong acid. But here's a diagram right there of what's actually happening. So you have HCl, which has the kind of covalent ionic bond. When you put it in water, that lone pair is going to attack hydrogen, and it's going to bind to where that lone pair was. So you have hydronium, still a tetrahedral structure, but now instead of bent, we would say this is trigonal pyramidal. And then you have the chloride ion floating around. Now, Arrhenius base, as I said, will increase the concentration of hydroxide, so just NaOH, just Na plus and OH minus. The same way, bases can be classified as strong or weak based on their dissociation. Strong bases: NaOH, LiOH, KOH, RbOH, CCMOH. All of those are just group 1 bases. Then we have 3 out of the 5 group 2 bases. Calcium hydroxide, strontium hydroxide, and barium hydroxide are strong bases. That leaves off magnesium and beryllium are not. And that actually has to do with solubility, not dissociation. They won't dissolve fully in water, and so they won't completely dissociate. And some of these are dibasic. So note that when calcium hydroxide dissolves, it doesn't produce 1 mole of OH, it produces 2. It breaks apart, leaving 2 ions of CaOH. Just the same way as, like, if we said, what is the Van 't Hoff factor when chapter 13, when we talked about our freezing point depression? For LiOH, you would say this breaks apart into 2 molecules, the Li and the OH. The calcium hydroxide would break apart into 3, 1 Ca2 plus and 2 OH1 minuses. So just note those guys are going to be a little weird if we deal with them. But however, there's many of the weak bases out there that derive from ammonia and will react thusly. NH3, in the presence of water, will produce ammonium and OH minus. So even though OH minus isn't in the ammonium, it produces ammonium upon reaction with water. The splitting of water in this way is called hydrolysis, Greek for literally loosening of water. So ammonia doesn't really, it's not easy to read by Arrhenius definition. Not so easy to understand by Arrhenius definition. So we're going to move directly into the Bronsted-Lowry, which is the most common one we're going to use for the majority of this chapter. Now, the Bronsted-Lowry definition, rather than having two different definitions depending on whether you're having acid or base, we're going to define Bronsted-Lowry only in terms of the acid. We're going to say, how does the acid react under acid and base conditions? So we're only going to look about this in terms of a proton. Under the Bronsted-Lowry definition, an acid will donate a proton. Whenever you lose a proton, you're an acid. Thus, a base must then accept a proton. Whenever you accept a proton, you will be a base. So everything we talked about before, still an acid. But now it allows us to understand what's called a conjugate acid-base pair, because all of these reactions are, in fact, reversible. Some of them are going to be very poorly reversible, meaning for when the Ka is really big, it doesn't want to reverse. But you could make it reverse under certain conditions. But if every acid will donate a proton, in the reverse reaction, it would have to accept that proton to go back. So every time you have an acid on the left, you're going to be generating a base on the right. And there's always going to be this pair. So let's look at this. HF, which is a weak acid, when it reacts with water, it's going to donate a proton to go to F minus. So HF is the obvious acid. Well, water, because it's accepting that proton, must be considered a base. Water is accepting that proton to go to hydronium. Now, looking at it from the other side, hydronium donating the proton to F minus to get back. Hydronium, when it goes from H3O to H2O, it is losing a H. When it loses that H, it is acting as an acid. F minus, to go back to HF, must be accepting an H. So F minus must be acting as a base. So looking at the pair, HF is the acid, F minus is its conjugate base, its paired base. H2O is the base, and H3O plus is its conjugate acid. Looking at ammonia and water, ammonia is our base, water is our acid. In the process here, ammonia is accepting a H from the acid to go to NH4. That makes that a base because it's accepting a proton when it goes from 3 to 4. And water is losing a proton to go from 2 to 1, from 2 hydrogens to 1 hydrogen. So this water is acting as an acid to get to the base. So we have water's acid-base pair, ammonia and ammonium as the base-acid pair. Now, water is a special molecule, as you may have noticed. Compounds like water can act either as an acid or a base, depending on the circumstances. These are called amphiprotic. Amphiprotic means I'm trying to remember, but it's essentially, it could go either way. It can either accept a proton or donate a proton, depending on the conditions. If we were to go into really heavy-duty inorganic chemistry, any molecule can be amphiprotic, depending on how strong acid or base it's used in. However, almost all the chemistry we will do will be in water. because water is the solvent. Water is the guy that's going to be the amphiprotic in all the cases we're going to deal with. But if I put ammonia as my solvent and I put a strong acid in ammonia, ammonia is going to accept the H. If I put a very strong base in ammonia, ammonia could act as an acid. But we're not going to deal with ammonia as a solvent. Okay. Now, each acid will have a vary in strength based on its degree of dissociation in water. Strong acids will dissociate before weaker acids. Strong bases will dissociate before weaker bases. So if I put a strong acid and a weak acid in solution and put a base, the stronger acid reacts first, and then the weaker acid, and then the weakest acid. So if I had HCl mixed with carbonic acid, which is a weak acid, the HCl is going to be completely used up before the carbonic acid gets used up. Now, the beautiful thing about our conjugate acid-base pairs is the strength of the pair has an inverse relationship. And this has to do with K being a state function. K being a state function. So a very strong acid forms a very weak base. And a moderately strong acid forms a moderately weak base. And a weak acid will form a strong base. This is based on this will control the reverse of the reaction. The size of the K. Looking at this, so phosphoric acid, while being a weak acid, is a stronger acid than dihydrogen phosphate, which is a stronger acid than hydrogen phosphate. And phosphate itself is going to be the strong base. So I want to look at that real quick, a relationship, a Ka, Kb, the K forward versus the K reverse. I'm going to go to the doc cam real quick to just show you the whole state function thing, state functionality of this. Okay. Just the idea that let's just do, well, it doesn't even need to be a weak, well, we'll do the HF plus water goes to H3O plus, so that's liquid, aqueous, F minus aqueous. So setting up the forward reaction. Setting up the forward reaction of this. K of the forward reaction would be products over reactants. H3O over F minus over HF. And we're going to get to setting these up later. Now, we don't include the water because water is a pure liquid. Remember, we don't use pure liquids or pure solids in our equilibrium expression. We don't use pure liquids or pure solids in our equilibrium expression. So there's our forward reaction, where the KF is related to these guys over that. Well, what about the reverse reaction? Let's write up the reverse reaction. F minus aqueous plus H3O plus aqueous goes to HF, aqueous, and water, liquid. Let's say this is 1 over 100. So that's our equal to our KF, 1 over 100. We set this guy up. The K reverse is then going to be products HF over reactants, which is H3O plus times F minus. Now, if this was 1 over 100, then this guy, which is the direct inverse, would have to be 100 over 1. And so that way, Kf is going to be equal to 1 over Kr. That's the meaning of a state function right there. That it doesn't matter which way you go, they're going to be interrelated. That because this is the reverse reaction, we can just inverse our K value. So if this number is really small, the reverse reaction is going to be very big. If this number is very big, the reverse reaction is going to be very small. That has to do with the state functionality and how we set up the state function in general. But so like things like phosphoric acid is going to easily donate the first proton, might even donate the second proton a bit, but it's going to not donate the third proton because the amount of acid in the solution is going to control how far this actually dissociates. Now, as I said, water, besides being amphiprotic, it can act as something, can do something really amazing, which is how we're going to base all of our pH things on. Water can act as an acid and a base, depending on the situation. But the fact of the matter is, it will do that simultaneously with itself. You put water in water, which is pretty much any water solution, and it does this. It's called autoionization. 2 molecules of water will split into an acid and a base. This is a reversible reaction. In fact, it is a rapid reaction. So before you're like, well, how come I never noticed that when I'm drinking a cool glass of water, I'm drinking it's sour and bitter at the same time? Well, this is a quick reaction with a heavy dependence on the reverse, where we're staying mostly with water. So even though this dissociates, no water molecule stays ionized for very long. So we don't ever have a buildup of acid or base in solution. But the fact that water does this with itself allows us to figure out the equilibrium constant. And we're going to use this ability for water to understand all acids and bases in terms of water. So equilibrium constant is very small, and the majority of water exists as just neutral water. So this equilibrium expression we call the KW, standing for the equilibrium of water. Remember, we ignore pure solids, pure liquids. So for water, it's just acid times base over 1, because water squared is just gets crossed out because it's pure liquid. The KW at 25 degrees is 1 times 10 to the negative 14th. KW is 1 times 10 to the negative 14th. That's always going to be the case unless we're dealing with a different temperature. Remember, the only way to change an equilibrium value is to change the temperature. So this is going to be, since we do most things at room temperature, it's going to be more or less constant. But what does that mean in terms of us? Is that whenever we determine acidity, we'll also know something about basicity. The amount of acid present in water is going to be inversely proportional to the amount of base in water. There will never be an absence of either of them. So long as there's acid, there must be base. Now, it's all about concentration. Whenever you have a lot of acid, you have a very little amount of base. And thus, acid is the much greater concentration. Whenever we have a very large amount of base, we have very little acid. And so we can look at the things in terms of that. So whenever H3O concentration is greater than OH minus, We have acid solution whenever H3O concentration is less than OH minus, base. And whenever they are equal, which based on this, the square root, if they're the same, the square root of 10 to the negative 14th is 10 to the negative 7th molar, we say the solution is neutral. It's neither more acidic nor more basic. Now, it's possible to get that. It's not super flavorful. If you distill the water and remove all the ions and boil out all the CO2, you can get neutral pH water. But most of the time, we're drinking probably mildly acidic water. Not much. Not much. Maybe only 10 to the negative 6th or 10 to the negative 5th concentration of protons or hydroniums. But a little bit, because just think about it, that CO2, when it dissolves in water, it makes it mildly acidic. So if you've left water sitting out for any given amount of time, CO2 from the atmosphere can absorb into the water and make it mildly acidic. I mean, any soda is going to have a decent amount of acid in there, even if it's just citric acid or phosphoric acid, which is a weak acid they use as part of like a flavoring and preservative. Carbonation, the carbonic acid, all that makes it acidic, which is why they say that this is bad for your teeth, because you're drinking large amounts of acid that's going to eat away at calcium deposits in your teeth. But so this is where we're going to bring it to finally the math of this. Start with the math. The main thing we're going to use is the pH scale. You've probably heard of this at least one point or another in your life. The pH scale is a base 10 logarithm. Please note, up until now, we've always been using the natural log. The natural log is what we've been using for any of our logarithmic things. But right now, we're going to use a base 10 log, just the log log, not the ln log. The log log is a base 10 system that's going to convert a concentration into a number between 0 and 14. We use base 10 increments. For every factor of 10 we change by, the number goes up by 1 or down by 1. So we're going to make it a negative log of a concentration. So it's either negative log of H plus or negative log of H3O plus. It's essentially the same thing. Because remember, we're going to use proton and hydronium essentially interchangeably. But pH is the negative log of the concentration of acid. Now, because of the Kw, we range from 0 to 14, with neutral water being when H plus is at 10 to the negative 7th, the negative log of 10 to the negative 7th is positive 7. So right between 0 and 14 is that middle point of 7. So whenever we have pH 7 water, it is neutral. Now, because of the negative log and the understanding of concentrations, the lower the number, the more acidic it is. So if I increase the concentration of acid from 10 to the negative 7th to 10 to the negative 5th, so this is more acid than base, negative log of 10 to the negative 5th is going to be 5. So 5 is less than 7. Whenever the pH goes down on the scale, we get more acidic. If I increase the amount of base to, like, say, instead of 10 to the negative 7th to 10 to the negative 3rd, that means the amount of acid would have to be 10 to the negative 11th. And with that in mind, the negative log of 10 to the negative 11th is 11. So when we have a lot of base, the pH would be 11. So whenever the pH is above 7, it is basic. But the pH in the P in pH stands for power function. So pH is a power function of the hydrogen concentration. We're going to see that P in several other different situations, but all the time it's going to be a power function of whatever follows that P. So when calculating a pH, only the digits after the decimal are actually significant. The ones and tens digit comes from the power function itself. So typically, if the concentration is 0.075, how many sig figs do you have? Well, it's a decimal. We start with the 7 and work our way backwards. So there's 2 sig figs. If I take the negative log of that number, it would be 7.5 times 10 to the negative second. The number would give you 1.12. The 1 is not significant. That 1 actually comes from that 10 to the negative second power. The 1.2 comes from the fact it's 7.5. The 2 sig figs there correlate to the 2 sig figs there. If I have 2.38 times 10 to the negative 11, we have 3 sig figs right there, 238. So if I took the negative log of that, it's going to be 10.623. I'm going to keep 3 sig figs after the decimal. After the decimal. So I'm probably not going to call you too much on sig figs, but if this comes up on the homework where you get it wrong when you think you've done it right, it might be about sig figs. Most of the time, your number is either going to be to 2 sig figs, 2 decimal points, or 3 decimal points. It will rarely be more than that when we do a negative log. But don't round this unnecessarily. Don't go, well, 2.38, that's 3 sig figs, so I'm going to round it to 10.6. 10.6, then you've cut off 2 of your sig figs. You've gone from 3 sig figs to 1 sig fig. But okay. So we're going to start doing some math in a minute. There should be a practice problem, but if pH is defined as negative log H plus, how do we get pH back into concentration? This is going to be something that will be asked. So here's some quick logarithmic relationships. If you've done this, you should have done this in math. I hope you've done this in math. But log x of y equals some z. Well, then x to the zth power gives you y. The inverse, we're essentially doing the inverse log function. Well, the inverse of a base 10 log is 10 to the power. So 10 to the power. So 10 to the power of pH. So this is because 10 to the power of log 10 of y is y. But in order to do this, we have to flip the sign. Since this is a negative log, we have to do 10 to the power of negative pH. So if 10 to the negative 7th equals 7, then to get back to 10 to the negative 7th, we're going to have 10 to the power of negative 7. In the case back there of 0.075, we're going to have 10 to the negative 1.12 will get us back our 0.075 again. 10 to the negative 1.12 gives us our 0.075. Oh, geez. Yeah, it'd take forever to get to homework problems because I want to be able to show all this. One last thing. If I don't have homework in the next, if I don't have some problems on the next slide, I'm going to take a break and do some homework, do some problems. But POH, if we can do pH, we can also do POH. Just like pH deals with the concentration of H plus. POH deals with the concentration of OH minus. And remember that KW relates H plus and OH minus. Thus, POH and pH are similarly related. Because if I take the negative log of 10 to the negative 14th, negative log of H plus, and negative log of OH minus, what we get, negative log of H plus becomes pH, negative log of OH minus becomes POH. Negative log of 10 to the negative 14th is 14. So basically, 14 equals pH plus POH. So if the pH of a solution is 3, the POH of that same solution must be 11, because 3 plus 11 adds up to 14. Because we're looking at the concentrations of each, when the number is low, below 7, it is favoring that thing. If it's high, it is disfavoring. So if pH is low, pH must be high. Both mean it's acidic. If pH is high, POH is low, it must mean it's basic. But no matter what, both of them can be interconverted with very little effort as long as you can do some simple algebra. Once you have pH, you can turn it to POH. The hardest part will be the log or inverse log. However, make sure you know which is being asked for in the answer and whether you start with an acid or a base. Otherwise, you can get well off the scale. So in this case, I ask you for what is the pH of 3.3 molar, 8.30 molar HCl? What's the pH of 4.0 times 10 to the negative 4th molar HI? And 5.2 times 10 to the negative 2nd molar NaOH. So let's go to the doc cam. Okay. So starting with our simple one. No matter what, when we get pH, pH equals negative log of H plus. With a strong acid, it is literally just going to be negative log base 10 of 0.30. You simply have to plug that into your calculator. You might need a half. Oh, thank God I have my calculator. I almost forgot this. So log, well, actually, sorry. I can do the negative log later, or I can do it now. Log of 0.30 gives me, notice it'll give me a ton of numbers. But I want to keep 2 sig figs because I have 2 sig figs. So 0.52. 0.52. That is incredibly acidic. Incredibly acidic. We've probably dealt with a concentration like that. The next one, HI, also an acid. So we just have to take negative log of 4.0 times 10 to the negative 4th. So once again, just negative log 4.0, 10 root negative 4, parentheses. Now this one is a little bit more dilute. Even though HI is also a strong acid, it is 3 pH units, actually 3.40, 3979 rounds up to 40. Because there is 2 sig figs here, I'm keeping these 2 sig figs there. Now the last one, it is a base. So if I take the negative log of this, I can take the negative log of this. However, this equation does not tell me what this gives me. You have to realize negative log of this concentration will be the pOH, not the pH, because this is the amount of acid I have. This is the amount of acid I have. This is the amount of base that would be generated. So if I take the negative log of that number, I'm going to get a suitably low number. But that is the amount of base, not the amount of acid. And when I ask for the pH, I'm saying, what is the amount of acid? So 1.28 pOH, how do we switch that? Well, 14 equals pH plus 1.28, or pOH. So how do we get the pH? I'm going to say 14 minus 1.28. So our pH is going to be 12.72 pH. So that is what we have to do in order to get pH of a base. You could have done this. You could have done this as well. Kw divided by OH minus gives you H plus. And then done the negative log. You would have gone the same answer. However, that's a little bit harder, honestly. It's a little bit harder because you have to do 10 to the negative 14, then divided by your 5.2 times 10 root negative 2, and then taking the negative log of that, you would still gotten 12.72. However, as I said, it's a little bit harder because you have to do more power function work. I do believe there's another practice problem. Okay. So watch out for that. That is an easy way to trip people up. Easy way to be tripped up. You don't think about that. I could just as easily ask, what is the pOH of 0.7 molar HCl? I could say, what is the H plus concentration of 12.30 pH LiOH? And then I ask, what is the OH minus concentration of that? Okay. Okay, let's look at that. Okay. So, once again, starting with there, pH equals the negative log of H plus, which is going to be the negative log of 0.7. I'm going to pretend I had a second sig fig, but I don't. Okay, now one sig fig will just one sig fig. Negative log of 0.7 is going to be 0.2 pH. 14 equals 0.2 plus pOH. So to get pOH, I'm going to subtract 0.2 from 14. So pOH equals, obviously, 13.8 pOH. Now working our way backwards, we have a base. We have a base, so the concentration of acid is going to be very small. If pH equals negative log of H plus, then H plus is going to be the opposite. So the first thing I do, I flip the sign to be negative pH. And then I do the inverse log of both sides. So inverse log gets me the 10 to the power of negative pH. So I'm going to have 10 to the power of negative 12.30. So second 10, negative 12.3. Plug into that in, hit enter. I get a number that's 5.0 times 10 to the negative 13th molar. So the concentration of acid in this base is really, really small. That's fine because it is a base. The amount of acid that's in that base should not be big. Now, in order to get the amount of OH in that same solution, OH, there's two ways you could do this. We can take Kw divided by H plus, and that will give us OH minus. That is what I will do. However, if you think about this and you can reason this out, you can say 14 minus 12.3 gives us the POH, and then go the 10 to the negative POH will give us our OH minus. Now, normally I would go with this method. This method would be easier mathematically, at least for me. However, since we already have this number, we can do this in one step rather than two steps. So I'm going to go ahead and go with this method. But both of them will give us the same number if done correctly. 5.0 times 10 to the negative 13. Guaranteed, because of how this is set up, this number will be not greater than 1, but pretty close to 1. Notice I'm putting this in parentheses to make sure I have this correct. Oh. Let's see. Yeah, syntax error. Got to make sure I click down before I end the parentheses. My answer is 0.02 molar. So the amount of LiOH, the concentration of LiOH in the 12.3 pH is 0.20 molar. The concentration of base in there is 0.020 molar. Yeah, I know I'm kind of... So be used to these simple things before we get too far, because we will get to some serious Ka expressions in a bit. However, we want to make sure we understand the basic conversions before we get to the more complicated ones. All of these are dealing with strong acids, strong bases. Now, one of the labs we will do, God knows when we'll get there, because things that kind of got slowed down, is we will measure some pH. We've done this before in lab, but we've only done this colorimetrically. But we can also do this potentiometrically. So I'll skip straight to the colorimetric one real quick. The colorimetric one, essentially, there's many different ways to do this. There is certain dyes that essentially under certain pHs will either become protonated or deprotonated. So they'll either accept an acid or be removed by a base, depending on whether there's more acid or more base in solution. This change in the proton count will change how this absorbs wavelengths of light, and thus it will change color. The one you have seen for sure is the phenolphthalein, which goes colorless in the presence of acid, and it turns pink in the presence of base. The second you add too much base, it essentially loses its proton, and suddenly it absorbs a different wavelength of light based on how the electrons move throughout this complicated molecule. And it absorbs the pinkish reddish dye. Now, there's a variety of different colorimetric things that will change at different pHs. Some of them will go from like green to yellow, or red to blue, or a variety of different colors. I mean, it all depends on what one you're using and what pH you need it to change at. There's also certain types of paper. The simplest of this paper will just turn red or blue depending on whether it's acidic or basic. There's blue paper that under base stays blue. Under acid, it will turn red where it's been dipped in acid. The red version of that paper will stay red in acid and turn blue in base. But some really fancy ones will actually turn a wide variety of colors based on the actual concentration. And they'll have a little color spectrum guide that you can hold up to it and see what pH it is. In fact, one of our online labs will deal with this, that cabbage, red cabbage actually is very pH sensitive. There's plenty of plants that are like this. If you distill out the cabbage juice, you can essentially test it on various pHs, and it'll turn various shades from like green to purple, green and yellow to purple, depending on your pH. And then you can actually put random solutions in there and say, what pH is this, comparing on the scale. I'm trying to remember if it's rhododendrons or certain types of like dogwood. It's like, I know I have some flowers in my backyard. I just don't know what is, but they'll be blue or red depending on the pH of the soil. What? Well, I might know what tulips probably as well, but I'm saying there's like a flowering shrub. They'll do that as well. But I mean, so depending on what pH of the soil is, you could look at various different colors that it takes up into the petals. But the other way, the way we'll actually be measuring in lab for the most part, is potentiometrically. And it's essentially a glorified millivoltometer. It's going to detect a current in solution. The current is going to be calibrated based on the amount of protons in solution. When we dip it in solution, it's going to detect the proton count and come out with a millivolt meter, say a voltage reading. However, we're going to calibrate it using between 2 to 3 standards of the, if this is the voltage reading under this pH standard, and this is the voltage reading under this pH standard, it can draw a linear relationship and tell you somewhat accurately what is the exact pH based on, like, if this concentration is this voltage and this concentration is this voltage, what concentration must this unknown voltage be? Or what unknown concentration will this known voltage be? And so that's what we're going to be doing. We're going to learn how to calibrate that, and then you can say, oh, this is the actual concentration of acid, which will allow us to measure the concentration point at points other than the stopping point. Previously, with the colorimetric titration, you kind of knew when it switched from acid to base based on a big jump. However, this will allow us to measure it the whole way through. and not just at the exact neutral middle point. So that is the overall goal. Now, I'm going to go ahead and look at some homework right now of this, because rather than get into weak acids just yet, I'll give you a break. I have no doubt we're probably at least a little bit ahead of the notes. So we'll look at some of the homework in a second. I got to get that going just so we can have more practice on this before we get into the weak acids. But just know when we get to the weak acids will have to do with the weak acids will essentially be a extension on our equilibrium values. So all the stuff we've done with equilibrium so far can now be applied to acid-base chemistry. In fact, there might be a couple simplistic acid-base problems on the test. But the idea is that if you do not know and understand the basics of Chapter 15, we need to make sure you do. We need to make sure we get this, because it doesn't go away. Equilibrium does not go away. It will stick with us, Chapter 16, Chapter 17. It will kind of go away a bit in Chapter 18 and then show up again as a surprise guest at the end. You won't need it till the very end, but it will show up again. The same thing with Chapter 19. We will think it's gone, but then it'll be back. Don't forget, there is some homework due tonight, Chapter 15, I think. But once again, just be working on the stuff. I want to try to keep you going on it. Don't expect you to be masters of it just yet. So, quick reminder. So lab this week, it's going to be a chance to make up any missed labs, get any help on the test, any help on the homework, catch up on any of that. If you don't have time to bug me outside of lecture. So the first thing I ask you to do in this one is just determine the conjugate acid, conjugate base pair. So literally for the conjugate acid and the conjugate base, to calculate a conjugate base, you will literally just remove a proton, and then by removing a proton, you change the charge by a factor of 1. So H3PO4 is neutral. So to remove a proton, it goes from H3PO4 to H2PO4 power of -1. Because if it was neutral before, when you subtract a positive, you get a negative. Conjugate base of HPO42 minus, if I remove a proton, it goes to PO4 3 minus, because it was 2 minus before, 2 negative, minus 1 is 3 negative. NH4 plus goes to NH3. We subtracted 1 from +1. We got neutral. So we can just leave it as neutral. If you were asked the conjugate base, you would just do the reverse. You would add a proton to each one, and the charge would go up by 1. Identify the product identify the product of an acid-base reaction. You have to look at First, identify whether HNO2 is an acid or a base. This will help you determine whether the amphiprotic substance is HSO4 or base of the reaction. So HNO2 is nitrous acid. HSO4 is can be amphiprotic. So we got to look at that. That one might take a try or two. But okay, write the balanced chemical equation. Okay. Ka and Kb for HSO3. So that one we can't do yet. I mean, technically you probably could, but we're not going to get to that just yet. Let's see. Okay, this one's closer to what we've been talking about. Okay, calculate H3O plus concentration given this amount of OH. Calculate the OH given this amount. Calculate the OH minus given that amount. And then we say which of these solutions are basic at 25 degrees. So let's look at 1.25 times 10 to the negative 7th. We have 9.89 times 10 to the negative 9th. And 0.0030619. 619. That's H3O. That's H3O. That's OH minus. Okay. Now, going from there to the doc cam. Literally, all you have to do is 10 to the negative 14th divided by whatever number we have right there. Divided by, so 10 root negative 14 divided by, in this case, 1.25 times 10 root negative 7. That would give us 8.0 times 10 4 6 10 to the negative 8.0 times 10 to the negative 8th. I don't know why I didn't put it in scientific, but that's the amount of H3O plus in my first problem. Now the next one. 10 root negative 14 divided by 9. Oh, God. Gotta make sure your calculator is working for you. 9.89 times 10 root negative 9. This is the amount of base. 1.01 times. Why is it not going into scientific? One, two, three, four, five, 6. 10 to the negative 6th molar OH. Last one. 10 root negative 14 divided by 0.000619. And that would give us 1.62 times 10 to the negative 11th molar OH. Then it asks us which one of these solutions are basic at that temperature. So to be basic, the OH concentration must be greater than 10 to the negative 7th. Specifically 1 times 10 to the negative 7th. Now, got to remember, 10 to the negative 6th even though you think -6 is smaller than -7, you got to remember this is negative logs. So -6 is actually 10 times greater concentration. If it was +6, you would be right, but -6. So this one is wrong. Now this one, 1.25, is technically greater than 1. It's not much greater than 1, but it is greater than 1. So 1 times 10 to the -7. So 1.25 molar OH is greater than 1 times 10 to the -7. So the first solution is basic. The second solution is basic in my example. So I'll put these values in, but you gotta make sure you know whether you're solving for acid or base. In this case, to answer this one, I can look at this right away and know, oh, that is basic. This one, you actually have to do the math to figure out, oh, that is basic. You could be able to think it out, but yeah, that is basic. So that's all the time we have. We'll look at a little bit more of this chapter and work on Thursday. Thank you for your time.